In every corner of our modern world, there's a silent force shaping the way we understand randomness, prediction, and even human behavior. This force is rooted in a mathematical breakthrough born from rivalry, obsession, and a relentless pursuit of truth. From shuffling a deck of cards to building the internet's most powerful search engine, it all traces back to a century-old feud that sparked one of the most important mathematical concepts ever discovered. The story begins in Russia, 1905. The country was on the brink of revolution. Socialist groups were rising against the Tsar, demanding sweeping reforms or the complete dismantling of his power. This division seeped into every aspect of society, politics, culture, and even the hallowed halls of academia. On one side stood the Tsarists, fiercely loyal to the existing order. On the other side, the socialists, hungry for change. Amidst this storm, mathematics itself became a battlefield. Defending the Tsar's side was Pavel Nekrasov, known as the Tsar of Probability. Nekrasov believed mathematics could explain divine will and even free will itself. His religious convictions fueled his arguments, tying the abstract world of numbers to spiritual beliefs. But opposite him was Andrey Markov, a man known for his fiery personality and unwavering commitment to logic. Nicknamed Andrey the Furious, Markov was an atheist and had no patience for what he considered the misuse of mathematics. To him, Nekrasov's ideas were absurd, even dangerous. Their feud centered on a fundamental concept in probability theory, the law of large numbers. This principle states that as you repeat an independent event, like flipping a coin, the results will eventually balance out to the expected ratio. Flip a fair coin 10 times, and you might get 6 heads and 4 tails. But flip it 1,000 times, and the result will converge to roughly 50-50. This idea, proven by Jacob Bernoulli in 1713, was the cornerstone of probability for nearly 2 centuries. However, there was one problem. Bernoulli's law applied only to independent events. What if events weren't independent? What if one outcome influenced the next? Nekrasov insisted that the law of large numbers required independence, and worse, he claimed that observing such patterns in social statistics, like marriage or crime rates, proved that these decisions were acts of free will. He pointed to the steady statistics of Belgian marriages as evidence that human choices were independent, and therefore measurable signs of free will. Markov was outraged. To him, Nekrasov's reasoning was a misuse of mathematics. He set out to prove him wrong, not just with words, but with something concrete, a mathematical model that could handle dependent events. To demonstrate this, Markov turned to the structure of language itself. He took the Russian poem Eugene Onegin by Alexander Pushkin and analyzed its first 20,000 letters. He discovered that letters weren't independent. Certain letters were far more likely to follow others. By analyzing these patterns, he developed a revolutionary tool, the Markov chain. The Markov chain allowed him to predict outcomes in systems where each step depends on the previous one. He showed that even dependent systems could follow the law of large numbers, utterly dismantling Nekrasov's claim. This was a turning point. Suddenly, probability wasn't limited to coin flips or dice rolls. It could be applied to real-world systems, from language to weather patterns. Yet Markov's discovery wasn't immediately celebrated. In fact, for years it remained obscure, a hidden gem of mathematical theory. Markov himself seemed indifferent to its practical applications, writing that he was focused purely on analysis rather than real-world problems. But as history would prove, his work would eventually reshape science, technology, and even warfare. Fast forward to 1945, the world had entered the nuclear age. On July 16th, the first atomic bomb, nicknamed the Gadget, detonated in the New Mexico desert, unleashing a blast equivalent to 25,000 tons of TNT. Behind this terrifying breakthrough were some of the greatest scientific minds of the era, including a little-known mathematician named Stanislaw Ulam. Ulam's work focused on understanding neutron behavior inside a nuclear core. Each neutron could collide with uranium atoms, split them, and release even more neutrons, a chain reaction that, if sustained, would cause a nuclear explosion. But predicting this behavior wasn't easy. The sheer number of interactions inside a nuclear core was astronomical, making precise calculations almost impossible. While recovering from a serious illness in early 1946, Ulam passed time playing solitaire. He began to wonder, what were the odds of winning a randomly shuffled game? The complexity of calculating every possible card arrangement seemed hopeless, but then he had a flash of inspiration. What if, instead of trying to compute the exact answer, he simply simulated hundreds of games and counted the wins? This approach would give him a statistical approximation. When Ulam returned to Los Alamos, he shared his idea with John von Neumann. Together, they applied this method to model neutron behavior in nuclear reactions. But they faced a challenge. The process wasn't independent, like shuffling cards. The outcome of each step depended on what came before. To solve this, they turned to Markov's forgotten concept, Markov chains. By modeling neutron behavior as a Markov chain, they could simulate countless possible scenarios and calculate the average outcomes. This approach, powered by the world's first electronic computer, ENIAC, gave them a powerful tool to approximate otherwise impossible calculations. The method became known as the Monte Carlo method, named after the famous casino in Monaco, a nod to the role of randomness in the process. This breakthrough changed everything. What started as a card game experiment became a cornerstone of modern science, influencing fields from nuclear physics to finance. But the story didn't end there. In the 90s, as the internet exploded, a new challenge emerged: how to navigate the ever-growing sea of information. Early search engines like Yahoo ranked web pages based simply on keyword frequency, a crude system that was easily manipulated. A page could stuff itself with repeated keywords to appear relevant, even if its content was worthless. The need for a better solution led two Stanford PhD students, Sergey Brin and Larry Page, to rethink how search engines should work. They realized that the web could be modeled as a giant Markov chain. Each web page was a state, and every hyperlink acted as a transition to another state. By running this chain and analyzing where a random surfer would spend the most time, they could rank pages not just by relevance, but by quality. This idea became the foundation of PageRank, the algorithm that powered Google. With PageRank, Google delivered better search results than any competitor, quickly rising to dominate the web. By 1998, Google had overtaken Yahoo, and today it's a $2 trillion giant, its core algorithms still relying on the principles of Markov chains. The influence of Markov's work extends even further. Claude Shannon, the father of information theory, used Markov chains to model and predict sequences of letters and words. This concept evolved into modern predictive text systems and, ultimately, the large language models that shape today's AI. However, even these systems have limitations. Feedback loops, like AI models training on content generated by other AI, can lead to a collapse in originality and diversity. Similarly, complex systems like climate change, where feedback loops amplify outcomes, remain challenging to model even with Markovian methods. Despite these challenges, the power of Markov chains lies in their simplicity. By focusing only on the current state and not the entire history, they make sense of systems that might otherwise seem too complex to predict. And all of this, the randomness of shuffling cards, the destructive force of nuclear weapons, the rise of Google, and the predictive power of AI, can be traced back to one man's determination to prove his rival wrong. As for the original question that sparked Ulam's curiosity, how many times must you shuffle a deck of cards to make it a truly random? The answer is 7 riffle shuffles. Anything less and patterns still remain. It's a fitting metaphor for Markov's work. Just as a deck of cards needs enough mixing to reach true randomness, Our understanding of the world needs the right tools to uncover its hidden patterns.